We can test products, but normal practice is to cut and machine a test piece. And you can see they can either be flat test pieces or machined from bar. A test piece allows controlled and observable measurements. We want to know where it's going to fail. We want to know what to measure in the area of failure. Now, going back to the previous module on elastic and plastic behavior, we learned that depending on its strength, a filament will stretch, that is, elongate under the hanging weight. The heavier the weight, the greater the stress, so the stretch of the filament. So stress is thus a function of load hanging on the object and the cross-sectional area of that object, of the filament. So far, we have talked about load and force, but these are not engineering measures. So we cannot design with these measures, nor indeed design with them. We need to define a measurable unit of force. Now, the unit of force we use is called the Newton, and its symbol is N. In the SI unit, it is the SI, the Standards International Unit of Force. It is named after Sir Isaac Newton because of his work on classical mechanics. The Newton is the force resultant from the action of gravity on a 1 kilogram weight. So a 1 kilogram weight hanging under the effect of gravity is a Newton. So this gives a Newton. So a Newton has a value of 9.81 newtons. The action of gravity on a 1 kilogram weight. Now the Newton gives us a measure of force, but as we have seen with the effect of a weight hanging on a filament, for engineering design, the area of the cross-sectional area of the filament has to be considered. The Pascal symbol PA is named after the French polymath Blaise Pascal, and the Pascal is the SI derived unit of pressure used to quantify stress. So the Pascal is defined as 1 Newton per square meter. Remember that a force hanging on the filament has a function of the cross-sectional area of the filament. So Pascal is defined as 1 Newton per square meter. The tensile force, the Newton, is the measure of force of load applied to a filament of a component. To determine the stress, we need to divide the force by the cross-sectional area of the filament. Stress, sigma, is the tensile force, sorry. Stress, sigma, is the tensile force, and Fn is divided by the nominal cross-sectional area of the specimen. So if we divide the applied force, newtons, through cross-sectional area, we have an engineering unit of stress. So we have a stress, force N, and if we divide it by the cross-sectional area of the filament, the part we're testing, in millimeters, square millimeters, we have a stress. So the units of engineering stress are measured in newtons per square millimeter, or more correctly, megapascals. We measure and design and stress in megapascals. If you know the yield stress of a component and multiply the value by the cross-sectional area of that component, this gives us the force that is required for that component to yield. So tensile stress is the applied force divided by the cross-sectional area, the force being in newtons divided by square millimeters, and that gives us stress, and stress is measured in megapascals. We now need to consider engineering strain. An engineering strain is a measure of the stretch of ductility or the elongation. Now, in a tensile test, we measure plastic deformation in terms of the cross-beam movements, but that's not an engineering measurement. Engineering strain is the measurement of the stress or ductility or elongation. So after the tensile test, we piece together the broken test piece. We can measure the plastic deformation, and then we can quantify the plastic deformation as a percentage of the original gauge length. And here's some further reading. I trust you can now understand plastic and elastic deformation and the tensile test. Thank you very much.